Hello and welcome back. What we were discussing in the last couple of hours of study was an interesting topic that is known as the genetic algorithm. We took in a deep inspiration from the biological world, where we said that the way humans interact and they produce their offspring that ultimately interact as well produce their offspring, and the offspring start getting better and better along with time. So what we said that can we take an inspiration, have some kind of problem that is our environment, produce solutions or the individual to this environment, and we do something, we make these solutions interact with each other and they start getting better and better and better along with time. So that was what the basic inspiration. We said that the numerous discussion on how different things would happen, what would be the complete algorithm, comprising of the mutation operator, the selection operator, the scaling operator, and so many operators. And what we were able to do is that we were able to build in some kind of framework in which all this was made possible. Today we continue our discussion with the same thing, and we do some kind of, I use the word analysis of this kind of algorithm that we make. We call it as the genetic algorithm. Now, fitness function was being used to assign fitness to any individual, let's say S. This is what gave me the fitness function of it. So let me make it a space over here, similar to the optimization space that we made the previous time, that again comprises of a number of dimensions denoting the number of parameters in the genotypic representation of the individual. So let's say if my solution S is nothing but it's I1, Si2 to Sij. This is what my solution Si is. So Sin. So I draw in an n plus 1 dimensional space where the base is of n dimensions. So this would be some S1 over here, there will be some S2 over here, there will be all S3, S4 over here, Sn over here. It will be a multi-dimensional space, and what I will plot it against is the fitness value. So what I am trying to do is that I am trying to plot this highly dimensional space of n plus 1 dimensions, and based on that I am trying to say is that can I draw in some kind of space. So again, space constraints, I can only draw a 2-dimensional plot, actually a 3-dimensional plot on this board, which will be visible as a 2-dimensional plot. And let me say that when I draw this plot, my plot is something of the order of, let's say this. This is what is known as the fitness landscape. Again, that has almost the same meaning as the optimization space which we have been discussing for the optimization problem since long. Now I plotted up for a problem of maximi, where the problem is to maximize the fitness function over here. If it would have been something like a minimization problem, I would have plotted the same thing, something like this, where the motivation was to find out this point, that is my global minima, and everything would have remained the same, but I could have called this as my cost landscape, only for some better understanding of the terms. We always minimize the cost and we always maximize the fitness. Sometimes you actually plot this up and call this a fitness landscape, and many times you say that we intend to minimize the fitness, and that is something like, as per English, that is wrong. You never minimize the fitness, you always minimize the cost. So whenever you use the term fitness, it naturally means that you are trying to maximize it. If by any chance you are trying to minimize it, don't use, just change the term fitness by the word cost, and everything will remain the same. Now again, I have plotted this very nice fitness fitness landscape over here, but what is important to realize are two things. Number one, in reality this plot can never be plotted. There are so many dimensions or combinations of it. It might be a high dimensional problem, might be the resolution of the landscape needed is too high for a very sensitive kind of problem where the curve keeps on fluctuating between the axes as you go along. So might be because of that I cannot draw the space. Or of course might be that the dimensionality is so high that I won't be able to graphically plot it up at any time. Even if I had tools to visualize at n plus 1 dimensional space. The other thing important to realize is that it may not be as perfect as shown. Many times the fitness landscape is like this. So there are some discontinuities in between. It's not differentiable. Many times the fitness landscape is like this. You do not know what lies between these regions. It's complete space, it's complete blank. Fitness cannot be found out. Many times the fitness landscape may be like this. Non-differentiable, non-continuous. Because if things were perfectly continuous, perfectly differentiable, why wouldn't we have used these statistical techniques and some kind of basic boundary agent approach over it to escape from the global minima, escape from the local minima? That would have given us good solutions. But the point is that not all fitness landscapes would be differentiable, not all of them would be continuous in nature, not all of them would be perfectly smooth in nature. Sometimes they would fluctuate a lot. I can have for very complex problem fitness landscape that span across like this, where there are multiple local minimas and one local minima. And of course, I am using the word cost landscape over here. It's all a fitness landscape. So still let's say that some kind of visualization is possible. So in order to better visualize the genetic algorithms, let me say I have already plotted this out. A multi-agent approach, so my solutions may be like this. Let me say I took so many solutions. Let me say they are all like this. Now again, the equivalent of it in non-discontinuous, non-differentiable, complex, simple fitness landscapes, it can be visualized. What I am drawing is a very simple case. Of course, if you take this kind of landscape as well, about it, the fitness landscape like this, again might be that these statistical techniques are much better to offer, but then I am only going this simple case only for easy visualization. What every solution I can do is I can find out its fitness value by a simple call to the fitness function. So for all of these, I know what the fitness value is all about. I have some kind of idea of what the fitness value is all about. What eventually happens in such kind of multi-agent approach that move on the basis of the genetic algorithm, what ultimately happens is that these all individuals, after one iteration of time, after one generation, they move. After one iteration of time, after one generation, what will happen is that they would move in this fitness landscape. This motion is by the operators of selection, that again has its corresponding scaling importance, playing a very important role to it. Mutation and crossover. So I know that the bad few individuals are not deleted. So let me say at any time, if I move on, this will get ultimately deleted, this might get deleted, this might get deleted as well. The fitter ones of them, they get selected multiple times for multiple operators. So let me say that let me apply crossover over here first. Let me say these two had a crossover, they produce an offspring over here. These two cross over, they produce over here. Let me say these two had a crossover, they produced an offspring, let's say over here. This was a contribution of what is known as the crossover. Again, let me say that there was some kind of mutation. This was selected for mutation, this produced an offspring here. This was selected for mutation, this produced an offspring over here. Let me again say this got selected for mutation, it got selected over here, and this was the elite. So my circles represent the old kind of the older values of the individuals, the older value of places where the individuals were located. My crosses represent where the new individuals are found in this fitness landscape. Now for better visualization, let me draw only the base of this curve over here and let me represent any individual by a dot. So I had this as S1, I had this as S2. Let me say this was S1, this was S2. A bound space, so I'll have some kind of bounds over here. And of course all the other spaces lie in between. All the various other space axes lie in between. So this is also a multi-dimensional graph. What we are seeing it from the top of it, and of course I can only represent it 2D dimension over here. So all the individuals would lie something like this: S1, S2, S3, let me say, and S4, S5, S6. These are what the circles are, and so on up till Sn. What ultimately I say is that this solution was the fittest. So let me say the solution is nothing but S2 over here. This is what the fittest solution is. So this goes straight away, and then I have solutions being produced like this. A crossover of this and this being produced here, a crossover of this and this being produced here, a crossover of this and this being produced here, this and this being produced here, and elite of this being produced here, and elite of this being produced here. So what would happen after this, and that is extremely important to realize, what would eventually happen out after this is the fact that I take a mean of all these individuals out here at any generation G. Let me say that I take in a mean of all the individuals at any generation G, and that mean is nothing but that denotes what the mean position is all about, where the mean position is there. Along with this mean, I take up a kind of standard deviation of the individuals. I say, oh, what is the kind of deviation that they have. So based on mean and standard deviation, when I analyze this thing, when I had circles, my mean was somewhere around this, and this is where the individuals were all spread around. When I say crosses, this is where the mean is, and this is what approximately the standard deviation is. So two things. Firstly, what has happened after application of one generation, what has happened after the application of just a single generation is that the mean has slowly moved towards the minima, the global minima. Let me say global minima was somewhere around here. After one generation, the mean has slowly moved around the global minima. Let me say here is when the mean would be somewhere around here, and after one generation the mean of all these would be somewhere, let's say, around here. So the mean is slowly moving towards the global minima. The other thing is that we call it as the search space is contracting. And what do I mean when I say is that the search space is contracting? Earlier, my global minima could lie anywhere between this. Now, my global minima lies anywhere inside this. Next time, it will lie anywhere between this, and so on. So these two things, they always happen. Firstly, the best in the mean position of these individuals, it starts getting moved towards the global minima. And secondly, the search space kind of contracts. Now these are two interesting little facts, and therefore we study it up to a little more extent is that why is it that it is happening? Now again, let me consider a random fitness space over here and a random little distribution of points over here at any generation G. I say where these odd points are. Now the genetic algorithm does not know what this landscape is all about. It does not at all know how this landscape is all about because it does not measure fitness at each and every point. All it knows is that what is the kind of fitness value enjoyed by its various individuals and what are their location in the fitness landscape. So let me say at this point of time all it knew was something like this. These are the only regions in the fitness landscape that our genetic algorithm knew. It always assumes that there would be a simple little connection between them and the actual fitness landscape would be something like this, and as it can be found out, that's not exactly like this, but it's something to do like this. What it does next is that it says, it assumes rather, that the individuals having bad fitness value, this entire region is not good. So this entire region is not good. These individuals act as kind of representatives of the space to which they belong. They act as representatives of the space to which they belong, and therefore if this individual has a bad fitness value, the genetic algorithm would automatically assume the entire region surrounded by this has a bad fitness value. And therefore that entire region is not to be looked at. And of course it will assume that this is what is known as a good region. So these individuals are automatically deleted, and then there is a competition between the regions of the individuals having some kind of good lying at this good region. Now what happens is that the fitter individuals attract the weaker individuals. So let me say that there were a number of points over here that were in this good region. The fitter ones will attract the weaker ones. The attraction power of any individual will be proportional to its fitness value. And now because we have had some bit of inspiration from what the basic genetic algorithm is all about, so let me correct the statement and say that the attraction power of an individual would be proportional to its expectation value. So these individuals would be the most attractive. And of course these would be the least attractive. So these two individuals, they drastically try to attract the other individuals towards themselves. It's a force by which they try to pull up the individuals towards themselves, and as a result new offsprings they produce very much close to all these individuals. The new individuals will be formed very much close to these individuals. They are badly trying to attract these individuals. And what we know is this attraction is nothing but the application of crossover. Now remember the same kind of fundamental that we applied. We first said that the selection of the best individuals, so good region being identified, and then attraction, where we know that the stronger individuals they get selected multiple times, and that's why I say that they have a larger level of attraction. And that is why that ultimately these individuals would be formed up somewhere here, much close towards the fitter individuals. So all that happens is that my crossover at every span of time is responsible for contraction of the search space. Now again a very good terminology that I use, contraction of the search space. Please realize that if you fitness landscape and place of individuals over there, it is assumed that whatever I can search up is what is surrounded by these individuals. So if my fitness landscape has individuals only at these places, I cannot go probably more than this. If my optima lies anywhere in this region, I am less and less likely to get that. Always I assume is that the optima, that is a maxima in case of a fitness landscape and a minima in case of a cost landscape, lies somewhere surrounded by, in the region that is surrounded by this individual. So what happens when the fitness landscape contracts is that my entire search space gets reduced. Earlier I had to find out my optima, that is a maxima in case of a fitness landscape in this entire region. Now I have to only find in this entire region because of some kind of contraction. And again, crossover is the operator that is doing this contraction. And again, the same principles that they apply because of these being more attractive in nature. But only contraction is a problem. It will be like having some magnetic forces in which the individuals, they start popping up towards the fittest individual, they start getting popping up, and after every hop, might be a new individual is found that is more, that has the best fitness value, and then all start popping up towards them. What ultimately happens is that in these kinds of problems, the optima is located here. The maxima is located here, but all these individuals, they are trying to hop up towards this individual initially. In this hopping up, we might eventually have an individual being produced somewhere out here. They hop up towards this individual, and then they contract up somewhere where all the individuals, they line up over here. Now it's continuous attraction by this individual out here. When all the individuals are taking a jump towards this individual, they line up somewhere in this fitness landscape. They may land up at better places like this and this, but ultimately they all at some amount of time be present in this entire region over here, and that is when my search space is nothing but a small point like this. That's what my search space contracts to. Now remember, in one iteration I had gone from this much large search space to this space. Next time I'll go up to this, next time I'll go up to this. I may contract out somewhere. And of course, this is not what the global optima is all about. That is not at all the global optima that lies. So if working with crossover alone, I unfortunately have this kind of problem in nature where all the individuals are likely to have accumulated over a point in some very few generations. Look at the speed in which the optima is converging, and to something like that. When you ideally search for optima kind of thing, a maxima over here is something that is more exploratory in nature. You say that you are the best individual, please try to look at what your surroundings are. When you look at your surroundings, you can probably try to say that this is a better place. So maybe you want to jump up over there. You might say that this is a worse place, so stay away from them. So it's some kind of exploration that is needed, where any individual over here explores what his surroundings are. It tries to take small steps ahead, small steps behind, and everywhere to try to find out whether it can get better places. And this exploration is what is provided by the mutation operator. So every individual takes in small steps ahead and behind to try to find out how it might get into better places in and around its vicinity. Now whenever I said that crossover results in this kind of convergence, that in genetic algorithm is known as a premature convergence. premature convergence, what ultimately happens is that my algorithm has no good because surface is very small. That is what is removed by this very contradictory operator known as mutation operator. One thing that I have already said is that it's exploratory in nature, where mostly the fitter individuals, they explore their space. The amount of space they explore, and the space is all by box, is what is known as the mutation strength or the mutation rate. If this rate is very high, it will try to take a large jump to find out what the fitness value is there. It will try to jump forward, backward, left, right, and all these spaces in this high dimensional space to find out what kind of fitness landscape is over there. If I make the mutation rate very low, it will take only small and small amounts of steps. And at every generation, it is only allowed to take one step, whose range may lie anyway from 0 towards the maximum value allowed by the mutation rate. So there is some kind of threshold over there. Now what mutation rate does, apart from this exploratory nature, is that it results in an expansion of search space. So because of my crossover rate, my search space was kind of contracting, and because of mutation, it will expand again. Why do I say it will expand again is that because every individual is trying to take a walk. Every individual is trying to take a walk. In this walk, it may go around at regions that are outside the vicinity of all the individuals, and therefore the search space expands. My mutation is a random step in any direction, and therefore it may take a step outside what is allowed by the present individuals, outside the scope of the present individuals. Again, I say that I am trying to, wherever my individuals are bound, that space I bound it as my search space. If my individuals are very much nearby, I will draw a curve around all these individuals and I will say this is my search space. So what mutation does is that it gives this S to the power to jump outside, and therefore the mutation is applied. It results in some kind of expansion. So the rate at which this contraction happens is determined by the crossover rate. Crossover rate determines what kind of contraction happens in this kind of search space. The kind of expansion that happens is determined by the mutation rate. Now normally the crossover rate is much higher than the mutation rate, and therefore I say that the search space always contracts. The search space always contracts because the mutation rate is always, crossover rate is always higher than mutation rate. This might be of the order of, let's say, 0.7. This might be of the order of, let's say, maximum 0.1. So therefore my crossover rate is always higher than my mutation rate. So my contraction is always larger than my expansion. And therefore what happens is that slowly and slowly all the individuals, they start converging at some point of time. Now again let me take in, because I used not many terms over here, now let me again go up into this kind of landscape. What would happen in this kind of landscape is natural that these are more attractive, so individuals being found over here, and later this will try to explore all this area. At some amount of time it will move up from here to here. It will try to move this way, it will try to move up from here to exactly this place. Now whenever it tries to move up from here to here, then we know it has got a better value. Of course there was always a chance it goes backward. It goes back along with time, but then its identity is always same because of the application of elite operator. So there will one individual always be here, and some point of time it will jump up from here to here. The hops are random. Some again point of time it will jump up from here to here, and so on. That is what the mutation does. Now again let me come up back towards this landscape that I had drawn. Let me say my individuals are at these locations. when initially my individuals are so wide apart, what happens is that crossover contracts this kind of search space into what is known as this search space. Let me say this was where the global minima was about. It will try to contract this space into this space towards the initial generations. Mutation will try to expand it a little, so let me say it got expanded up to this rim over here. That is almost the same thing, a very minor kind of expansion that happened. This is known as the mutation rate, the expansion that can maximum happen. Now I'm drawing this very small because mostly these individuals will be participating in this mutation rate and they'll maximum move across this over here, or sometimes this over here. So the expansion is very small. But what would happen at later stages of time is that the same space being plotted, towards the end, this is what the surface is, what mutation, what crossover will get. From this it will try to contract it towards this. But now the mutation rate is constant, that's the same amount of distance my one individual can move. The same amount of distance that my one individual can move. So let me say the same amount of individual, the best fitness over here moves. And that is what results in almost an equal, sometimes a larger and sometimes a smaller kind of expansion. This is what will result in some kind of expansion over here. So here you see that crossover is not denoting anything. The individuals over here may have almost the same value. It's just trying to attract individuals what is already converged. The mutation is trying to explore up the entire space. Mutation is trying to explore the entire space. Because the same distance that it had moved over here, the same distance it will move over here. Now let me further go along with time and say that all the individuals have kind of converged into some point now. Now crossover will hardly result in anything, all the individuals are at same places. My mutation can move the individual in any of these directions. This amount is fixed, the maximum that an individual moves. So here the contraction is much less. Of course there's nothing to contract, you already contracted, but the expansion is much more. So mutation will try to expand, it will again get contracted by the mutation. What would eventually happen is, this was my global minima, let's say here this is my global minima. From the crossover I can never reach this global minima because I will be bound by the space over here that recognizes all the individuals. By only the application of the crossover I will not be able to reach up this global minima over here because my crossover always produces individuals in between the individuals that are selected for crossover. It always produces individuals in between the individuals that are ultimately selected for this kind of crossover thing. And hence, there is a limitation that I have got that my new offspring will also be generated somewhere in between, they cannot generate outside this space. But mutation can move this entire space. So what happens that, when there was a problem of premature convergence over here, that in this space, this was a global minima, but unfortunately all the individuals they got selected over, individuals they got collected out at this point here. My mutation operator, it will try to move this entire space first from here to let's say here, then from here to let's say here, then from here to here, and here to here. So after a premature convergence, there is an exploration that happens that is initiated by the mutation operator. Now again, the amount of space this moves is determined by mutation rate. So if the mutation rate is very small, this movements would be very small in nature. If the mutation rate is very large, the movements would be so large that it might overjump the global minima. From here it might come up here, from here it might come up here, from here it might come up here, from here it might come up here. It will keep oscillating around this region, but it will never come onto this. And almost a similar thing we studied in learning later in the neural networks, where we said that large amount of learning overshoot the minima, and it will keep the system will keep oscillating like this. The system will keep oscillating like this. Here the system will oscillate from here to here, from here to here, from here to here, from here to let's say here, because the mutation rate is low, high. And again, if the mutation rate, learning rate is low, my algorithm slowly and slowly goes up over here, and like this also it will slowly and slowly go up over here towards the global minimum. If my crossover rate is very high, there will always be a premature convergence. From here it will contract to anywhere between here, depending on where the fittest individual is. That will be more and more attractive if there is a crossover rate is high. And in that case, my premature convergence will be at the point that is way apart from the global minima. So let's say global minima was here, my premature convergence happened over here from high crossover rate. If my crossover rate is low, all these individuals, they'll be very slow in jumping towards this best individual so far, or the high fitness individuals. They'll be very slow. They'll take in very slow walks from their places towards the global minima. So based on, I'll do away with this, I'll do away with this. In fact, I'll do away with this. So again, let me say what must be already clear. The motivation of it is already there. If I take in any population at any time, I take any population at any time, let's say T. T represents the generation. I find out the best individual. That is, I see all the individuals and I say this one is the best of it all. The individual having the best fitness value. So I say best individual B at any time T. That is equal to the individual at any time T such that the fitness of SIT is greater than any other individual SJT for all J not equal to I. I find out the worst individual, let's say W at any time T, that is equal to again an individual SI such that the fitness of SIT is greater than or that of SJT is less than. For all J not equal to I find out the average fitness. I find out what the average individual is about. That is exactly its location at the fitness landscape. That is the mean position in the fitness landscape. So I say that the average fitness, I say A at any time T is nothing but summation of SIT for all I divided by the number of individuals N. I find out what is the best fitness. I say FB at the time T is equals to the fitness of the best individual. I find out the worst fitness. That I say WT. That is fitness of the worst individuals at any time T. I say that what is the average fitness. I say average fitness at any time T, that is equal to summation I upon N, I1 to N. My fitness of SIT. I have these kinds of metrics with me. Now again I will be repeating what we already studied in terms of these three metrics. My best individual, my average individual, it will always move towards the global minima. First there will be a kind of convergence that unfortunately may be a premature convergence. So it will be, that will define my position in the entire landscape. I do it over here, and then my mutation will take it closer and closer towards the global minima. The same would be with my best fitness, where my individual will slowly and slowly go towards the global minima, and my worst fitness, that again will move towards the global minima because the surface is contracting. The location where it's found, it will change up drastically towards the starting, but then it will ultimately lie closer and closer towards the global minima, only because my crossover rate is higher than the mutation rate, and there is a contraction in surface that happens towards the global minima, around the global minima. And after the convergence has already taken place, there is an exploration by the mutation that takes it towards the global minima. But what is interesting are these three parameters, my best fitness and worst fitness and average fitness, what we normally observe when we plot a graph for any time t. Now I am using the word fitness over here. So what will happen is that my worst fitness, it will be very small towards the starting, it will be very small towards the starting, and ultimately it will constantly increase. It will constantly increase, something like this. My best fitness, it will be reasonably high towards the starting, it will also increase something like this. And my average fitness would be intermediate. So let me say something like this. For any all generation G. This means that the individuals are all at different places on this fitness landscape. All the individuals are at different places in the fitness landscape. What this means is that they have converged. And why there is a slight gap in between them? Because the mutation is always pushing in individuals. Mutation is always pushing in individuals. So my worst fitness is not equal to the best fitness, because the moment my worst fitness equals to best fitness, that means all the individuals lying at the point, the mutation operator will make one jump at some degree. It will make one of the individual jump, and therefore my worst fitness will by some magnitude deteriorate, the magnitude depending upon my mutation rate. If my worst fitness deteriorates, my average fitness again is going to change. And hence, this is what the trend that is observed. The basic inspiration that we took even at the previous hour of lecture, we took it today as well. How the Darwinian principle of selection of the best, how the principle of a high crossover rate that results in convergence, and how the application of a mutation rate that expands and results in some kind of explosion leads to this kind of fitness landscape that we all observe. So again, I'll touch upon the entire thing. Let me denote another point over here. So if this was again my individuals, this was S1, this was S2, I introduce the term as diversity. I coin in a new term known as diversity. Diversity denotes my average separation between individuals. So I say that diversity is what is inside this fitness landscape, the average separation between two individuals. How are two individuals at an average separated from each other? So I draw in three landscapes like this. These are the two, and this is the third. Here the average separation would be very high. All the individuals are wide apart each other. So this is what is known as a high diversity fitness landscape. This is known as a moderate diversity. They are moderately apart. And this is what is a low diversity fitness landscape. And my diversity would be measured by summation of I1 to n, let's say j equal to I plus 1 to n, the separation between an individual Si and Sj, and there will be approximately n minus 1 by 2 addition. So to take out the average, I'll have to divide by the number of terms I have added up over here. So there will be approximately those many. Alternatively, you can always say that Si minus Sj, I equals to 1 to n, j equals to 1 to n divided by n square minus 1. That will be the number of relation over there. Automatically, you will get up to you towards the same thing. So this is what is known as the diversity. What happens in a genetic algorithm is that the diversity is very much wide apart at the starting generation. So let's say this was a generation, let's say 0 to 5. Then it drastically reduces. So let me say this was what was 6 to 10 and this is what was the 100th generation. They are all at the same place. The diversity, it continuously reduces. What is responsible for the reduction of diversity is again crossover, contraction, diversity loss. What prohibits loss of diversity is mutation, tries to expand the subspace. So that's what is the concept of diversity that we will be using in a lot of our discussion that is to follow. So I am into discussion of what is known as the diversity preservation. We'll study the diversity preservation first and then we'll come up to the schemata theory just after we finish off with the diversity preservation. That will be the last topic of the analysis. We will discuss some new topics after that. So let me say that there was a fitness landscape, so it must have a curve something like this, and might be, okay, I'm drawing a maxima. Let me say there was a fitness landscape. I'm drawing only the two dimension here for easy understanding. So let me say that there was something like this, followed up by something like this, and followed up by something like this. This is what is known as a global maxima. This is a local maxima, and this is a local maxima. Initially, my individuals are located here, 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 here. Let me say my initial is all random, so there are individuals like this at this point of time. Why this happened is that because my algorithm will always return me individuals that are randomly distributed, and here the probability distribution is equal. So there will be a lot of individuals here because they occupy a large space. There might be very few individuals over here because the space is much large. In fact, whatever I have drawn is also a large number. The space is very small, so this region will get very small number of individuals, this will get very small number of individuals. So as you can see, there were 6 over here, there were 4 over here, there were 3 over here. And naturally I will need to increase this over here because this region is very large. So by equal probability distribution, the number of individuals here will be very large. Now what happens is that I apply the same genetic operators, elite, this got selected, mutation. These have higher fitness values, so this got crossed over with this, it resulted in this. This got crossed over with this, it resulted in this. This got crossed over with this, it resulted in, let me say this got crossed over with this over here, it resulted in this. This got crossed over with this resulted in this, and so on. Now what you can see is that my subspace has got bound to this place, and the global maxima is out of picture now. The global maxima has completely gone out of picture over here now. Problem? Of course. Next time, these two will, and let me say that the mutation happened, so this mutated, it was somewhere around here, this mutated, it was somewhere around here, this mutated, it was somewhere around here, and so on. Next time, out of these, this will be more attracted, this will be more attracted, they generated all these kinds of individuals, they'll mutate, they'll go up over here, and ultimately, all these individuals, they will get converged over here towards a local maxima, which we know is not the answer to our problem. So why this kind of problem was caused? The first part of it that you cannot help because this region was very low, so there were very few individuals over here. This could have been still better, even though this local, but this region was again low, so there were very low individuals over here. This you cannot help, of course. It was very sensitive. The changes were very large at a very small amount of time. Again, you cannot help it. It's a property of a fitness landscape. It is an intrinsic property that the fitness landscape has and that you cannot change. And because you cannot change, you have to change in something else. So the other reason because of which that happened is that this crossover resulted in production of individuals here. This crossover resulted in production of individuals here. So these all at the time being had some low fitness and hence they got deleted. Because what the genetic algorithm ultimately presumed the landscape out of this was that the landscape would be something like this. It did not know that there was a spike over here and it was another spike over here. And hence my algorithm completely got off. So the solution is a very simple solution. The actual solution is a very simple solution, and that just states do not allow two contradictory individuals far apart the fitness landscape, that was in case of this and this, to cross over with each other. So we have something known as diversity preservation being applied to it. Diversity preservation states is that always preserve your diversity, do not let the diversity lose. Out here in this kind of fitness landscape, I only draw the base. It started off with this. This was the region where the global minima was there and only a couple of individuals, but it got converged into a local minima over here only because the individuals were small. What diversity preservation says is do not let your diversity lose. So never assume that far-lying areas, they actually become representatives of your fitness over here. Don't assume that the average fitness of this region is represented by these individuals. So if we apply diversity preservation, we prohibit these two individuals. As a result, this individual will only be allowed to interact with these individuals here. Only these individuals can have crossover between themselves. Only these regions can have crossover between themselves, and only these individuals can have crossover between themselves. And as a result, what would happen is that there would be three evolutionary processes. One at this region, one at this region, and the other, let's say, at this region. This was our first local minima, this was our second local minima, and this was our third local minima, this was a global minima. We have three completely different evolutionary processes, and as a result, these individuals will got crossover somewhere here, somewhere here, somewhere here. They got mutation somewhere here, like this. After some amount of time, after let's say 5 generations, what would happen is that the individuals here will get an average fitness value of this region. But after 5 generations, these individuals will be over here. So earlier this was attracting this and this. Now these individuals will attract this and this. And hence because of this attraction, we know what would happen is that once they reach this threshold, once the average individuals here they reach this threshold, they will be the ones participating in elite, so carbon copies being formed. They will be the ones mutating, so more carbon copies formed, because it's a kind of, we only apply restriction to the crossover, not the mutation and the elite. Only the fittest individual they participate in these operators. And as a result, when these individuals were out these regions, let me say out of 25 individuals, let me say some 15 were here, 5 were here, and 5 were here. When these individuals were at this region, these individuals were at this region. When this threshold crossed and a fit individuals comes up over here, because of being selected multiple times at mutation and crossover, the additional individuals being formed by mutation and crossover would be here, and those that would not survive because of the selection of the fittest individuals would be these ones. So these won't survive. So next time only 5 of them would die, and those 5 of them that would die here would be compensated by the mutation operators over here. Next time, more of them would die, so 5 of them would more die in the next generation and they would be compensated over here. Next time these would die, it will cause them this, so it will be compensated over here. So towards the end, they ultimately come up to the global maxima, which might be just a single individual left who will eventually die out in the next generation. So by this we know what is known as the diversity preservation, that is of extreme importance here. What we said that in this landscape, only let these 3 individuals survive. 3 independent processes of one of them dominates the other in terms of mutation alike. So ultimately the number of individuals, they'll keep getting over here and they'll keep getting lesser and lesser over here. Ultimately at some point of time these 2 may vanish. What the biological analogy is, they are Africans who have some characteristics, they are American who have some characteristics, they are Indian who have some characteristics. Don't let any one generation that is fit as per your evaluation die. Don't let the Americans die, don't let the Indians die, don't let the British die. Let them all have their own evolution. Once they have their own evolution, they are very much comfortable as per their local surroundings, as per their habitat. Then you have a global kind of vision and then you select the best individual. But surviving the characteristics of all these different races of people is important. You need to preserve all the different races and not let one race that is better only as per the current time over-dominate the other races. And hence, this is also known as something called as liking in evolutionary operators, liking in genetic algorithms. And that's what the entire picture says, like diversity preservation helps in escaping a local minima and getting converged to a global minima. That is what it helps in. That is what we get by diversity preservation. Again, which depends upon the sensitivity of the fitness landscape. We will touch upon the schemata theory into our next lecture.